Observe a weather system over the course of a week, and you are watching a system constantly shifting between distinct, observable conditions over time. Classical probability theory often focuses on isolated, static random variables. You calculate the odds of a single coin flip or a static die roll. But real-world systems, like regional weather patterns or global financial markets, are in constant motion. To model these dynamic systems, mathematicians rely on what is known as a stochastic process. In this framework, a random variable evolves through a specific sequence of discrete states across distinct time steps. This introduces a complex computational problem. If a system transitions randomly at every single step, predicting its long-term behavior requires accounting for an exploding number of possible paths. To solve this, we apply a mathematical assumption called the Markov property. It is a filter that cuts through the noise of historical data by declaring the past irrelevant to future predictions. By focusing only on the present state, the Markov property provides a mathematical engine to project long-term structural outcomes without needing the full history of the system. The first step in building a Markov model is defining the state space. This is the finite, exhaustive set of all possible values or conditions that a specific system can occupy. The formal definition of the Markov property states that the probability of the next state, x sub n plus 1, is conditioned solely on the current state, x sub n. The variables representing previous time steps are mathematically struck from the equation. This illustrates the Memoryless property. If the system is on the sunny node, the path taken over the last 5 days has zero impact on predicting tomorrow's weather. Memorylessness does not imply unpredictable chaos. The transitions between states are governed by specific, quantifiable probabilities that remain constant over time. Because the future depends entirely on the present, we can encode a system's entire dynamic behavior into a single computable matrix. Consider a heavy manufacturing facility. We can model a critical factory machine that operates in a state space of two conditions, working and broken. We map the daily transition probabilities. A working machine has a 95% chance of staying working tomorrow. If it breaks down, a repair crew ensures it has a 60% probability of returning to a working state the next day. To calculate future outcomes, we translate this visual node graph into a square grid called a transition matrix, denoted as P. Looking at this matrix, row 1 represents the working state, holding our 95% and 5% probabilities. Row 2 represents the broken state, populated with our 60 and 40% chances. Notice a strict mathematical rule at play. Every single row in a transition matrix must sum to exactly 1. At every time step, the system must transition somewhere, even if that means staying put. This matrix, P, acts as a complete blueprint for the system's one-step future. We now have the algebraic foundation required for long-term forecasting. Matrix P gives us the precise probability of the machine's state tomorrow. But how do we find the probability of its condition exactly 30 days from now? We calculate n-step transitions. Importantly, we do not multiply the matrix by n. We use linear algebra to multiply the matrix by itself, raising it to the nth power. P squared gives us the probabilities for 2 days out. By repeatedly multiplying the matrix, we propagate the system's dynamics forward in time, stepping further into the future with each multiplication. Watch the internal values as the exponent n becomes very large. The numbers shift and eventually lock into place. The two rows of the resulting matrix become completely identical, settling on 0.923 and 0.077. When the rows become identical, the math is telling us something specific. The initial starting state no longer affects the outcome. Whether the machine was working or broken on day 1 has zero mathematical bearing on day 50. Through repeated matrix multiplication, the system eventually discards its arbitrary starting conditions. What remains is a hidden long-term equilibrium. We define this long-run equilibrium formally as the stationary distribution. It is denoted by the Greek letter pi. Pi is a fixed probability distribution over the states. Once the system reaches this distribution, it remains completely unchanged even if you project it one more step forward in time. To find this without endless multiplication, we solve the algebraic equation pi equals pi times p, combined with the rule that the probabilities of all states must sum to 1. Solving this linear system isolates the probability for the broken state at roughly 0.0769. Interpreting this result gives us a deterministic metric. Over the long run, this specific machine will be broken approximately 7.7% of the time, allowing facility managers to accurately budget for maintenance. However, a unique steady state only exists if the Markov chain is well behaved. Specifically, the system must meet the mathematical condition of being irreducible. An irreducible system is one where every state can eventually be reached from every other state. If a system contains an absorbing state, like a defaulted loan where probability enters but never leaves, the probability mass eventually drains into that trap. This is the forward problem. By analyzing the transition rules of an irreducible system, we calculate its transition matrix and mathematically determine its final steady-state destination. So far, we have started with observable physical systems, constructed their transition matrices, and solved for their eventual steady states. Modern Bayesian statistics requires the opposite direction. In advanced machine learning, we often face an inverse problem. We already know the target probability distribution we want to analyze, the pi, but its geometric complexity makes it impossible to sample from directly. This creates a mathematical duality between studying a Markov chain and executing Markov chain Monte Carlo, or MCMC. The engineering logic of MCMC is highly specific. If we cannot sample from the complex distribution directly, we must intentionally design a transition matrix P, whose guaranteed steady state equals that exact complex distribution. We pivot from analyzing existing probabilities to reverse engineering our own transition rules. This conceptual shift is the computational mechanism powering modern machine learning. The most common mechanism used to construct this reverse-engineered matrix is the Metropolis-Hastings algorithm. This topography represents a multi-peaked probability distribution. We drop a particle at random coordinates, marking our current state, x. It projects a path to a candidate state, x prime. It then calculates an acceptance ratio, r, dividing the proposed state's density by the current state. The rule is strict. If the proposed move goes uphill into a zone of higher probability density, the ratio is greater than 1, and the algorithm automatically accepts the move. If the proposed move goes downhill, it is only accepted with a probability exactly equal to that ratio. This allows the chain to occasionally explore low probability valleys without getting trapped in a local peak. By enforcing this acceptance rule at every step, the particle's movement perfectly satisfies the steady-state equation. By enforcing this acceptance rule, the particle's movement satisfies the steady-state equation. We force the chain's long-term behavior to match the target topography. There is an operational reality to this process. Because the particle's starting position was chosen arbitrarily, the earliest steps of the chain do not accurately represent the target distribution. To correct for this, statisticians enforce a burn-in period. We let the algorithm run for thousands of iterations, intentionally discarding these early samples until the influence of the starting state fades. Once burn-in is complete, the chain has converged. Recording the particle's ongoing path from that point forward yields samples that accurately represent the intractable Bayesian posterior. Predicting a factory machine's failure rate and training complex AI models via MCMC seem like unrelated disciplines. Both systems are powered by the same engine. By proving that a system's future can be decoupled from its past, the Markov property provides a method to model and navigate complexity by focusing solely on the present.